So we just got through learning about air masses. Now we're going to move into storms and storm systems. And a really good place to start would be to ask, where do storms get their energy from? Well, they get it from two places. First and foremost, they get it from the solar heating of Earth's surface. They also get it through the release of latent heat during condensation. Remember that condensation is a warming process because as those hydrogen bonds are reformed, as water vapor condenses back into liquid droplets, that latent heat is released back to the atmosphere. And that is going to also, along with solar energy, help fuel storm development. So let's stop and take a second and just kind of get an idea of the spatiotemporal scale of all the different storms and systems that we're going to cover in this chapter. We go from very small and very brief to much, much longer time periods and larger scale storms, ranging from our single scale thunderstorms in your lower left-hand corner of this graph. These last only an hour or so, and they occupy very little geographic space. We're talking like maybe a kilometer or two. As we move up, those storm systems increase in size and time. And so we're going from those very small single cell thunderstorms to all the way to like El Nino and La Nina events. These take months to develop, can last more than a year, and have global effects. But we're going to start small. We're going to start with thunderstorms. First off, the single cell thunderstorm. Leading off with a few quick facts about thunderstorms. Thunderstorms are associated with cumulonimbus clouds. Remember those big, tall, towering clouds that produce lightning and thunder. Very important. If it's producing lightning and thunder out of a cumulonimbus cloud, it's a thunderstorm. Most thunderstorms that occur are embedded within spatially much larger scale systems like tropical cyclones, typhoons, hurricanes. That's all the same thing you will learn. Mid-latitude cyclones, and the ITCZ. Remember, the ITCZ is a discontinuous belt of thunderstorms all along roughly the equator. There are globally about 40,000 thunderstorms every single day over the face of the planet. The Earth is a buzzing place. Globally, these thunderstorms are most frequent in the tropics over land. If you're wondering why, well, think about what we just said gives those storms their energy. We have solar heating of the Earth and lots of available moisture in the atmosphere. And where do we get the most of that? That solar energy that's hitting the tropics provides the most solar heating, and especially over land, because the land heats up faster than the water. And there's a lot of ocean around the tropics, so we've got an abundant source of moisture. And you can see this in this thunderstorm frequency map. This is actually showing lightning flashes per square kilometer per year. Lightning indicates thunderstorm activity. That's the only way you're really going to get lightning. And the flash frequency density of lightning, how often they occur within a given area, gives us a really good indication of thunderstorm activity. About 70% of all the thunderstorms occur over land in the tropics, which you can see here. If we look at it, we've got our dark areas and areas in red are where you get the most thunderstorms. And across this whole map, the Congo Basin in Africa has the highest incidence of thunderstorms anywhere on the planet. Why? Well, okay, it's in the tropics. It's that land surface is heating up very rapidly. We have ocean on either side contributing moisture. The Congo is also covered in really thick jungles, so you have a lot of that transpiration from plants contributing to the available moisture. If we just look at North America, the U.S. Southeast has the highest frequency of thunderstorm activity, with the highest amount of it in Florida. Why Florida? Well, it's got ocean on three sides, and it's got lots of maritime tropical air masses coming in from the Gulf of Mexico. Thunderstorms will also form around frontal lines, which we're going to learn about in a later lecture. But remember those air masses. There are large regions of air very large, that have uniform characteristics of temperature and humidity. So where two air masses meet of very different characteristics of humidity and temperature, they will come together and they will clash, and they will cause a lot of storm development. We see this a lot, this particular scenario, east of the Rockies, and primarily in spring. And here's a map just supporting what I just said. This is the lightning flash density distribution across the United States. You can see that the heaviest activity is in the southeast region. That's because it is a very warm area and it has a lot of abundant moisture available in it because of that Gulf of Mexico. If we look over on the west coast, we'll see that this is what's going on. We have very, very little thunderstorm activity compared to the rest of the United States. This is our least active area. This is because of the cold Pacific current. That cold Pacific current does not evaporate moisture as readily as, say, like the Gulf of Mexico. So there's not as much moisture available. It tends to be drier. And it's because it's cold, we have really a lot of suppression of convective activity. So we just don't have the environment to produce a lot of thunderstorm activity. But then if you start moving eastward, you notice an uptick in the amount of activity right around central Colorado. This is because of the Rocky Mountains. Those mountains really enhance orographic uplift there, so we have that going on, if you remember your lifting mechanisms. We also have this area of a lot of continental polar air coming down and a lot of maritime tropical air coming up, meeting right around this one area just east of the Rockies. Typically in spring, we get a lot of thunderstorm activity. I would like to emphasize that you want to have a really good idea of what's going on thunderstorm-wise in these three different regions. This is a geography class, so it is extremely important to notice where things happened and why they happen where they do. So kind of know what is the thunderstorm activity like in each of these regions and why is it like that. Now, you may have noticed when we looked at that spatiotemporal graph about the different storm systems that there were several types of thunderstorms listed. We have three types, listing them in order of size and most often in terms of intensity too. We have single-cell thunderstorms, multicell thunderstorms, and supercell thunderstorms. Wind shear is the biggest contributing factor to whether a storm develops into a little baby single cell thunderstorm or it grows into a massive supercell thunderstorm. You may not be familiar with the name wind shear. So what that means is this is changes in wind speed and direction with altitude. We could be talking about wind at the surface is moving in one direction and wind above it in successive layers is moving in different directions. They could be moving at very different wind speeds. We could have combinations of both of those. Those changes in wind speed and direction, that wind shear is really going to sculpt the development of our thunderstorm. When we get lots and lots of atmospheric moisture and lots of wind shear going, we can turn that into a very impressive thunderstorm. First, let's look at the ingredients for a single cell thunderstorm, though. This is our smallest version of a thunderstorm. A single cell thunderstorm is exactly what it sounds like. It is a single thunderstorm. It is relatively mild and short-lived. They usually last about an hour. They form within maritime tropical air masses. It's very important to understand. The wind shear within these air masses is typically very weak. And single cell thunderstorms develop mainly from convective activity, from surface heating, if there is enough moisture around, and they tend to develop in the late afternoon. We see this a lot, warm days. With a single cell thunderstorm, they experience very predictable sequences of growth where they mature, they rain out, and then they die, or we say dissipate. Let's take a look at that. This figure walks you through that process of storm cloud development, thunderstorm development. From its beginning baby stages that forms a storm cloud to its mature stage to its dissipating stage, its old, decrepit old age, and eventual death. It's very sad. So, starting with the first stage, the cumulus stage. In this stage, the warm air parcel rises, it cools and condenses to form a cumulus cloud. Updrafts from the heated Earth's surface continue to build that cloud as it goes. That is what's causing its upward development. In the second stage, the mature stage, those updrafts from the surface continue, and they continue to build up the cloud. They strengthen, eventually reach a peak. Meanwhile, as the vapor has formed into droplets and starts to rain out, it causes downdrafts where air is flowing from the cloud down towards the surface. This causes really precipitation and really strong weather phenomena like lightning and thunder. And then our third dissipating stage, this is where those downdrafts dominate. There's more air coming down out of the cloud than there is going up. That cuts off our updrafts, which causes the storm to weaken and the cloud to eventually dissipate and just disappear. Once again, let's go over the stages of thunderstorm development marked in red because it might be something you need to know for the exam. We have our stage 1, which is the cumulus stage. We have stage 2, which is the mature stage. And we have stage 3, the dissipating stage. So we have the growth stage, the mature stage, and then the, so sad, the thunderstorm is dying out stage. Now, if we have moderate wind shear, wind shear that's stronger than what we get with a single cell type thunderstorm, we will get what are called multicellular thunderstorms. And those are just what they sound like. These are like connected little single cells, but connected to each other, one after the other. They typically form along fronts where that colder air is meeting that warmer air, where you actually see moving air at different temperatures, making the wind blow in many different directions. This causes that wind shear to increase and arranges those thunderstorms into little small clusters. You may have heard the term squall line before. Like you heard the news network meteorologists say, hey, we have a squall line approaching. This is just a line of multicell thunderstorms as they form along that cold front in that mid-latitude cyclone, which is something we will get into next lecture or the one after. This is just a graphic of a squall line and how that develops. You can read through how it develops, but basically when you have an updraft and a downdraft in a developing storm cloud and a lot of wind shear in the atmosphere, it's going to cause that initial single cell thunderstorm to tilt. And when it starts to tilt, it allows a little bit more space on its back end in order to create another cell right behind it. You can see this in the top of this image here, the creation of cell B and cell A behind that main cloud. Basically, as that first cloud is starting to die off, there are new clouds spawning behind it, just like zombies on Call of Duty. They just keep popping up. Now, these tend to happen most often, squall lines, when you have a large air mass of cold continental polar air moving into an area and displacing a lot of warm, wet maritime tropical air. What you're looking at here is a radar image of a squall line that occurred across the southeast It's a pretty impressive long squall line. This happened in November of 2016, and they do have this characteristic, very linear appearance because it's this long chain of continually spawning thunderstorms. Multicell thunderstorms often produce severe weather. You won't get a whole lot of really, really rough, severe weather from a single cell, but you will from a multicell and from supercells, which we'll learn about in just a minute. When we say severe weather, severe thunderstorm activity, we have a very specific definition. For a thunderstorm to be considered severe, it has to be one that produces hail of greater than 1 inch in diameter, or produces a tornado, or has wind gusts of greater than 58 miles per hour, or any combination of those three things. And then we get to our big guy, supercell thunderstorms. This is a really massive thunderstorm. It's not quite hurricane level, but it's way up there. This type of thunderstorm, a supercell, actually gets a rotating updraft. Remember, the updrafts are coming up from the surface up into the cloud to help build that. We get a rotating updraft. So now we have spin going inside the cloud. As you might imagine, this has potential for turning into a tornado. And in fact, almost all tornadoes are embedded in supercell thunderstorms. So let's take a look at supercell thunderstorm development. This is what I mean by an rotating updraft. When you have an environment with a lot of wind shear, it can actually cause the air at ground surface to begin to roll. And if that rolling air at ground surface happens to roll into an already forming updraft inside of a thunderstorm, it can cause that updraft to also begin to spin. This is known as a mesocyclone, highlighted in red. The problem with mesocyclones, they're not actually visible to the observer. So you can't see the internal structure of that updraft spinning just by looking at it. But I will show you when we get to the section on tornadoes how we might see it on radar to tell us that a tornado is coming. Your textbook has an image of a supercell that formed over Kadoka, South Dakota. This is a really great example of a region where supercell development would be most likely. This is where we get our supercells most commonly because they have all the right ingredients. But because I'm a big fan of the weird and wonderful and of Mother Nature and her constant ability to just yell, "Surprise!" I'm going to end this lecture with an image of a fairly impressive supercell. It's not South Dakota level, but it's fairly impressive, that happened to form in a place where we would least expect to see it, Northern California. Why there? Why would we not expect to see it there? Because that cold California current that flows along the west coast of the US produces an environment that is not conducive to supercell development. And yet there it is. Good one, Mother Nature. And with that, we're going to end this lecture, and next up, we will look at the lecture on lightning.